Hello guys, let's have a look at another question involving mechanics. We'll start with the question. Blocks of mass m and 2m are connected by a light string and placed on a frictionless inclined plane that makes an angle theta with the horizontal, as shown in figure 1 above. Another light string connecting the block of mass small m to a hanging sphere of mass capital M passes over a pulley of negligible mass and negligible friction. The entire system is initially at rest and in equilibrium. Here we understand that the bodies are in equilibrium, which in turn tells us that either the bodies are moving with constant velocity or they have net force equal to 0. The fact that they say at rest eliminates one of the possibilities, which tells us that the bodies are at rest. In other words, 0 velocity and 0 net force. Moving on to part A, on the dots below that represent the block of mass small m and the sphere of mass capital M, draw and label the forces, not components, that act on each of the objects shown. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Here we are necessarily drawing a free body diagram for the bodies. Now, starting with mass M, it has tension T2 acting up the slope. It has its weight W, which is equal to mg acting downwards. It has a normal force, also known as a reaction force. Let's call that N, acting perpendicular to the surface. And it has another tension T1 due to the wire being attached to the mass 2m. Looking at the other sphere has just the translated tension T2 seen here, and it has its own weight W is equal to capital M into G acting downwards. Moving ahead, derive your expressions for the magnitudes of each of the following. If you need to draw anything other than what you have shown in part A to assist your solution, use the space below. Do not add anything to the figures in part A. Now, here we are to derive an expression for the force T2, which is exerted on the block of mass M by the string. Express your answers in terms of small m, the angle of inclination for the inclined plane theta, and other physical constants as appropriate. Now, let's try to write a resultant force equation for the body small m. We have resultant force sigma F, which is equal to m into A, which is equivalent to the tension T2 minus. Now here we notice that when we are writing the equation with respect to T2, the bodies M and 2M can be assumed to be a single body of a combined mass 3m. And for this combined mass 3m, it has its gravitational force or the weight acting downwards, and the component of weight, which is 3 times m times g times sine theta acting down the slope, while its horizontal component acts perpendicular or opposite to the reaction force. Since we are writing the equation for tension, we only consider the component down the slope. So we write T2 minus m plus 2m times g times sine of theta. When simplified further, we get T2 is equal to 3 times m times g times sine of the angle theta. Moving on, we also want an equation for the mass capital M, for which the system can remain in equilibrium. Express your answers in terms of m, theta, and the physical constants as appropriate. Here we understand that the bodies stay in equilibrium as long as the tension T2 acting here will be exactly equal to the tension T2 acting here. From the free body diagram we've written for the sphere of mass capital M, we get the same equation. Resultant force sigma F, which is equal to MA, will be equivalent to 0, as is the previous case, will be equal to 0. This will again be equal to T2 minus capital M times G. Since the value of T2 is known, we substitute that, making the equation 3 times small m times G times sine of theta minus capital M times G is equal to 0, giving us the final expression for capital M as 3 times small m times sine of theta. Moving on. Now, suppose that the mass M is large enough to descend and that the sphere reaches the floor before the blocks reach the pulley. Answer the following for the moment immediately after the sphere reaches the floor. Now, due to tension T1, does tension T1 increase, decrease to a non-zero value, or decrease to 0, or stay the same? We understand that at the moment, that is immediately after the sphere reaches the floor, the tension T1 no longer ceases to exist, which means it will decrease to 0. Moving on, is the velocity of the block of mass small m up the ramp, down the ramp, or 0? At the moment immediately after the sphere reaches the floor, the motion of the body small m is still directed upwards, which means the velocity is also directed upwards or up the lamp. Moving on, is the acceleration of the block of mass m up the ramp, down the ramp, or 0? We understand that the acceleration of the block is always down the ramp. In fact, it's a component of acceleration due to gravity, g sine theta. Moving on to the last question. Consider the initial setup in figure 1. Now suppose the surface of incline is rough and the coefficient of static friction between the blocks and the inclined plane is μs. Derive an expression for the minimum possible value of capital M that will keep the blocks from moving down the incline. Express your answer in terms of M, μs, theta, and the fundamental constants as appropriate. We understand that the conditions existent before still prevail, while there is an additional frictional force. Let's call frictional force as Fs acting down the slope. The frictional force Fs acts down the slope since the bodies are or would be pulled up the slope in case of motion. Now, to the equations we wrote before for the resultant force, we make slight modifications. We write tension T2 minus the two combined masses, that is M plus 2M times G sine of theta minus the combined frictional force Fs for both the bodies M and 2M combined is now equivalent to 0. We know that friction has a standard formula. Fs is equal to mu into N, where N stands for the normal reaction. Since the normal reaction force N, as stated here, is exactly opposite to the component of weight, that is 3 mg cos theta, we can write the formula as Fs is equal to mu s into 3 times m times g times cosine of theta. With these substitutions, our final equation for tension T2 becomes equal to 3m times g times sine of theta plus mu s times 3 times m times g times cosine of theta. Moving ahead, we know that the same tension T2 also acts on the sphere of mass capital M, making sure that the tension T2 is also equal to the weight of the sphere, which is capital M times G. Simplifying further, we get capital M is equal to 3 times M taken common, and within the brackets we have sine of theta minus mu s into cosine of theta. This gives us the final required expression in terms of capital M.